Hello everyone and welcome to today's session where I will walk you through some basics of ARM64 architecture, where I will try to explain you about the architecture itself, the instruction sets, registers and the stack. And for this video I have specifically prepared this presentation to explain you about all the basics. So let's directly jump onto the topic. So let's begin with the introduction first. So, as some of you might already know, ARM64 is a family of RISC architecture. RISC architecture uses a small, highly optimized set of instructions rather than more specialized instruction set found in other architectures like CISC. ARM basically follows load and store approach, where all the operands and destination used by any instruction must be stored in the register. This load and store approach can be categorized into two parts. First one is memory access, which load and stores the data between memory and the registers. And the second one is ALU operations, which occurs only between registers. So the first approach is followed by CISC architecture, whereas the second approach is followed by RISC architecture. So for instance, in a load store approach, both operands and destination, let's say for an add operation, must be in registers. This differs from our register memory based architecture. For example, a CISC instruction set architecture such as x86, in which one of the operands for the add operation may be in memory while the other is in a register. So I hope by now you got some idea about the basic difference between RISC architecture and the CISC architecture. So using ARM, which is a RISC-based architecture for mobile devices and for IoT devices, is ideal as it requires fewer transistors and hence led to less power consumption and heating of the device, which obviously overall improves the battery life and hence appropriate for mobile devices. Okay, so understanding this architecture is therefore essential because nowadays all the mobile devices, whether you talk about iOS or Android or any other IoT device like Raspberry Pi, um, all of them are using ARM processors. Then next we have to understand that ARM64 is Little Indian. This means that the last byte of the data will be stored first. Let me try to explain it to you using this figure. So let's say we want to store this data into the memory, and let's assume that it's an integer value and we know that integer is of 4 bytes. So as per Little Indian convention, what will happen, last bytes will be stored first, right? So over here we have a continuous array of memory. So the last byte 67 will be stored first, followed by next bytes which is 45, then 23 and then 01. Okay, and Big Indian is the opposite of this. So it is possible to configure ARM processor in such a way that it uses Big Indian, but by default it uses Little Indian, and all our mobile devices follows Little Indian format. Then next we have 64-bit pointers and registers in ARM64. Since it's a 64-bit architecture, so all the memory addresses and the register size are 64 bits. And then there are in total 32 general purpose registers, including a zero register. Now, obviously, it is not possible to cover the whole ARM64 architecture in detail in this short video, and hence I will be focusing on the most useful topics of ARM. Also, I am planning to create a complete tutorial series for ARM64 architecture where I will cover all the instruction sets, registers, and I will also walk you through the assembly programming of it. So if you are interested, then please subscribe to my channel to get the latest updates. Okay, then let's move on to the next slide. So here we will discuss about different ARM registers in a little bit more detail depending on their usage. As I have already told you that we have in total 32 general purpose registers which we denote using XN or WN, where X stands for 64-bit and W stands for 32-bit, and this N range from 0 to 31. Let's say I want to use register 20 in 64-bit mode, so I will put X20. And this means that I am talking about 64-bit register, and if I say W20, then I am talking about 32-bit register. Now at hardware level, these two are not two different registers actually, but our one single 64-bit register is divided into two parts. If we want to access 32 bits of the register, then the lower half of the 64-bit register will be used, otherwise full 64-bit register will be used. Apart from this, one of the general purpose register is used as a zero register, which we can specifically denote using WZR or XZR, where W stands for 32-bit and X stands for 64-bit. And there are certain situations where we directly want to use zero value. So instead of manually moving zero into a register and then performing operation on it, we can directly use this XZR or WZR registers uh, to get the zero value. Then we have SP stack pointer. This is also 64 bits, and this always points to the top of the stack. Then let's come to the most important part of any architecture, which is calling convention. Now in this particular case I have um, this table which is applicable for Debian based operating system like Linux on which Android runs. So firstly we have X0 to X7 register. These are general purpose registers and used mainly for holding the parameters which are passed to the function. So in case if any function requires more than 8 parameters, the rest of the parameters will be stored on the stack. Then next we have X8 to X18. These are temporary registers for every function. Basically these registers will be used to store values of any arithmetic operation or any other instruction which needs a data to be stored for processing. Then next we have X19 to X28. So these are again general purpose registers which may or may not be used, and in case if used by a function must have their values preserved and later restored upon returning to the caller. Okay. Then we have X29 registers which we can also denote using FP, which stands for frame pointer, and this always points to the bottom of the frame. Then we have X30 register which again we can represent using LR link register, and this holds the return address of a function call. So the callee should always save this X30 or link register uh, if it intends to call a subroutine, so that later after completion of the subroutine it can come back to the previous instruction. Then we have X16. Now why I have specified it here specifically is because sometimes it is used for holding system calls. In ARM64 we have this SVC instruction which we can use to perform any system call. So all the functions have a specific or unique number assigned, which we can mention in this X16 register in order to use it with SVC instruction. Okay, next we have X31 register, which is multi-purpose register, and it holds uh, the value of a stack pointer or the zero register depending on the context of the program. Then next we have program counter register, and this register basically contains the address of the next instruction to be executed. Then we have our status registers represented as CPSR, and this is used to hold the flags like carry flag, zero flag, overflow flag, stuff like this. So on performing any arithmetic operation, depending on the results, these flag values will be either set or reset. Now, before moving forward, actually, I want to show you visually how the stacks looks like in memory and what all registers are used and how. So, if you consider this slide, in this figure specifically, you can see that there are two functions currently present in the stack, function 1 and function 2. So just note that function uses stack to save local variables and for preserving registers state. So to keep everything organized, function uses stack frame, which you can see here. Okay, so stack frame is a localized memory portion within the stack dedicated for a specific function. So here, this particular stack frame is specific to function 1. This stack frame gets created during the prologue of the function. So at the beginning of every function, we have this prologue part, and at the end of the function, we have epilogue. So during the prologue, this stack frame will be created. And as you can see here, the frame pointer is pointing to the bottom of the frame, and then the stack buffer is allocated for the stack. Now the stack frame is starting from its bottom, correct? So for this function 1, this stack frame is starting from the bottom, generally contains the parameter values, any register values which needs to be preserved, like link register which holds the return address, etc. Okay, so I hope you got a clear picture about how these special registers are used and how the stack looks like. And whenever any function gets called, it will be first pushed onto the stack, then the stack frame is created, and inside that stack frame, everything related to the function is present. So that's how it works in memory. Now after completion of the function, let's say the function 2 is executed, then this return value or the return address will be popped from the stack in order to let the CPU know that which instruction to execute next. Okay, great. Let's move forward. Then we have ARM64 opcodes. So here I have tried to show you the opcodes which you will encounter frequently during your pen testing or reverse engineering exercises. So the first one is move instruction. This instruction copies the value in a source register from the destination register. And the instruction looks something like this, where RD is the destination register and RN is the source register. So if we have an instruction which says move x0 comma x1, this basically means that the value of x1 register will be copied to x0 register. Similarly, we can use immediate values instead of the register. Okay. Then next we have move n instruction. This instruction is usually used for moving bit masks. Here n stands for negate. Let me try to explain you in a better way using an example. So let's say you want to move bit mask value this. okay, to X0 register. Now this value is 64 bits, and as per ARM architecture, you can't directly move immediate value of 64 bit into any register directly. Okay, so the limit for immediate values is 16 bit. So basically, first of all, we will take the first 2 bytes of this value, which is 0xFFFF, and we will perform left shift by 16. And if we perform left shift by 16 on this value, it will become 0x, and all of these f's will be turned into 0, and these zeros will be turned into f, and this f will be turned into zeros. Okay, and then that value will be negated, so you will get this value back in the x0 register. Next we have move k and move z. These two instructions are sometimes used one after the other, and that's why I am trying to explain you these two instructions together. They are used to move immediate values. Move Z moves an immediate value of 16 bit to a register, and all the other bits outside the immediate value are set to 0. So for example, over here you see move Z x0 comma 0x1f88. This is the immediate value which needs to be moved into x0 register. So our x0 register is 64 bit of length, okay, and this value is 2 bytes, which is 16. So the 16 bits will be filled by this value, and the remaining bits will be filled by 0, because this z denotes 0. Then we have move k. Move k moves an immediate value but leaves the other bits of the register untouched. So in this case, let's say we need to move this value into x0 register. Now again, directly we can't move this many bits into the register. So what we will do, we will make use of both of these instructions together. First we will perform move z instruction on 0x1f88. This will move this value into x0 register and fill the remaining bits with 0. Then this move k instruction, what it will do, we will move these 16 bits into x0 register, and since it will not change the remaining bits, so finally we will get this value in the x0 register. Then we have LSL and LSR instructions, which is our shift instruction. So LSL will perform logical shift left and LSR will perform logical shift right. The syntax is pretty easy to understand. Logical shift left, destination register, source register, and the number by which you want to perform the shift. Similarly for LSR, we have the same syntax. So after performing the shift, it will put the result into this RD register. Then we have LDR, which is load register. This will load a word or double word from memory and writes it to a register. The address that is used for the load is calculated from the base register and then immediate offset. So if you observe from the syntax, this is our destination register where the value will be stored, and by adding the base register and the immediate value, we will get the memory address from where the value can be loaded. Then next we have STR, which is exactly the opposite of LDR instructions. So here what it will do is it will store whatever the value is in the WT register to the memory address pointed out by this value. Okay, moving on to ADR and ADRP instruction. These are basically address of label or address of page at PC relative offset. So later we will see by example how these instructions can be used. Now let's focus on the remaining two instructions, which is CMP compare. This instruction will compare two values, and as per the result the flags are updated automatically. So the Z flag will be set if the result of the compare is 0. V flag will be set if the result of comparing the two values uh, will result in an overflow, and C if the value is smaller than the second operand. Then we have B and E, which stands for branch or not equal to. So if the 0 flag is not set, it will take the branch, otherwise it won't. Okay, let's come to the next slide where I will explain you about some examples on how the instructions are used, and these are some very basic and common instructions which you will encounter mostly in your binaries. So the first one is move x0 comma x1. This we have already seen what it will do. It will move the value of x1 register into x0 register. Then we have move n, where n stands for negate. So what it will do in simple words, it will negate this immediate value and put it into x0 register. Next we have add x0 comma x1. This is pretty straightforward to understand. It will add value of x0 and x1 and put the result into x0 register. So this is our destination register here. Then we have LDR load register, and as I have explained you earlier, it will move the value pointed by this x1 register into x0 register. So whatever the value present in the memory address of x1, that will be moved into x0. Then we have LDR x0 comma x1 comma 0x10. This is basically indexing mode, and that's how you will, and similar kind of instruction you will see if you write an array or something. So for indexing this is used. So what will happen here, the value of x1 will be added by 10, and whatever the result, that will be your memory address, and the value that is present on that memory address will be stored into x0 register. Then we have LDR x0 comma x1 square brackets comma 0x10. This is our post indexing mode. What this means basically is whatever the value pointed out by the memory address of x1 will be first stored into x0, and then x1 will be incremented by 0x10. Then we have STR, which is store register. It will store the value of this x0 register into the memory address pointed out by this x1 register. Okay, this I think we have already seen. Then we have LDRBW0, x1. Here, this is similar to load register, but we have specified this B, which stands for byte. So it will only load a byte from the address stored in x1 into W0 register. Then we have LDR-SB. So again, here this SB stands for sign bytes. So it will load a sign byte from the address stored in x1 to W0. Then we have ADRX0, label. This will load the address of labels into x0 register. Next we have this STP instruction. what it will do, it will take the value of this x0 register and put it into the memory address pointed by the x2 register, and then it will increment this x2 register by 1 and put the value of x1 register into that value. Then we have stp instruction again, um, where now instead of using the memory addresses we are going to put it onto the stack. So here the value of x29 and x30, which is our link register, will be stored into the stack. Okay, so I think I am done with some of the basic stuffs of ARM64 architecture. So thank you everyone for staying till the end with me, and in the next video I'm going to cover ARM binary emulation using Unicorn framework and all the basics which will be required related to ARM architecture we have covered in this video. So stay tuned for the next video and I hope to meet you all again.